We don't want to waste our rocket. It'll take us 3 years to make the rocket and only 15 minutes to use it. I don't want to waste my shot here.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this?
It is really, really challenging and nerve-wracking at that point.
At T-minus 1 minute, all of us ran out.
Hey everyone! Today we're live at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and we're here with a team of experts to talk about sounding rockets. Sounding rockets were NASA's first space vehicles, but they remain one of the agency's most important tools for cutting-edge science today. The footage you just saw was from a recent sounding rocket mission that launched last year from an island in the middle of the Arctic Ocean. But it was just the first mission of a larger series called the Grand Challenge Initiative CUSP. In fact, people are there right now, back on the island, preparing for launches that are coming up in just a week. Today, we'll be joined by scientists from that mission and other experts from NASA's Sounding Rockets program. Here's the show that we have for you today. First, we'll talk all about what sounding rockets are and the groundbreaking research that they've contributed to science. Next, we'll talk about what makes sounding rockets unique and why they can do science that no other launch vehicle can. We'll cover how sounding rockets are advancing space science and technology, and we'll take you inside NASA's Wallops Flight Facility, the place where it all happens. Finally, we'll go behind the scenes with an Arctic sounding rocket mission and learn what it's like to launch one. If you have any questions throughout the show, use the hashtag AskNASA in the comments, and we'll answer some of them later on. Stay with us. I'm now joined by Rob Pfaff, the project scientist for NASA's Sounding Rockets program, and a couple parts of sounding rockets. Rob, tell us a little bit more about what sounding rockets are and how they differ from other kinds of spacecraft.
Sure. Well, sounding rockets are spacecraft. They're launched into space by NASA to carry out scientific investigations and also to test new instruments. They differ from satellites in that satellites go into space and orbit the Earth, and they can last for many, many years, usually in one region, one altitude region. The sounding rockets, on the other hand, go up into space and come down. We call them suborbital platforms. So they follow parabolic trajectories, and it's a more limited time, only 10 or 15 minutes, but it's very focused investigations. I should say that NASA has had sounding rockets really since the onset of the agency over 60 years ago. They've served us very well in the scientific community, supporting such disciplines as astronomy, solar physics, and also geospace. Geospace is that region around the Earth that includes the ionosphere, the upper atmosphere. It's where, for example, the aurora is formed, and that region is ideal for study with sounding rockets. We also look at planetary re-entry systems and special projects such as that are served by the Sounding Rocket program. I just want to say, people are always asking me, why sounding rocket?
Right. That was
sounding is actually an old nautical term, which means to take measurements of the depth of the ocean below. You take soundings. And so essentially a sounding rocket is simply a rocket that takes measurements.
Got it. And we have a couple parts of a sounding rocket here in the studio. This one looks like it's a little worse for the wear. Tell me more about what this guy is.
Okay, this is a nose cone. It served us very well on a rocket that was launched from White Sands Missile Range, and that rocket was recovered, and the nose cone was also recovered. As you can see, it got a few dents. We would never fly this again, but nevertheless, this is what a nose cone looks like. The rocket over here, the payload over here on my left, has again the nose cone on top. This is one of our smaller payloads, and then this segment here includes the instruments and the telemetry system and batteries and that sort of thing. So this would then go on top of a motor, which of course isn't here with us in the studio.
So sounding rockets launch above the atmosphere, but why is it important to get above the atmosphere?
Well, it's extremely important, particularly in the fields of astronomy and solar physics, because you want to look at wavelengths which are absorbed by the atmosphere. So you have to, if you want to look at ultraviolet radiation, for example, you need to be above the atmosphere to look at those.
And you mentioned that they follow an elliptical trajectory, so they fall back down. And How much time do they actually get to do
Okay.
science?
Actually, it's a parabolic trajectory.
Okay, right.
And
Got
you get, depends on the apogee. You can get 5, 10, or maybe 15 minutes are typical.
Got it. That doesn't sound like much time, but sounding rockets can actually accomplish a lot in just a few minutes. Here's a brief video about the history of sounding rocket research, including some of the groundbreaking achievements that they've made.
We'd been flying instruments on balloons for decades. And the more we flew them, the more we learned about the atmosphere. But we couldn't go that high. And so we knew there was an awful lot more to discover.
Scientists started to develop rockets in the 1930s, but a big incentive to explore the upper atmosphere was during World War II, when the US captured Germany's V-2 rocket, a long-range missile that could fly to these upper regions. Seeing that the Germans had created this sophisticated rocket, scientists from the US Navy were motivated to learn how to build their own.
A number of the early sounding rocket technologies and the experiments that they're designed to do are largely for military applications.
They wanted to know the nature of that medium through which missiles would eventually travel. So the sounding rocket really became the vehicle of choice.
After years of proving the scientific worth of sounding rockets, in 1958, NASA's Sounding Rockets program was born. These small but versatile rockets have founded entirely new fields of science: ultraviolet, X-ray, and gamma-ray astronomy, which inevitably led to more discoveries. A sounding rocket made the first detection of molecular hydrogen in space. Sounding rockets confirmed the theory that the aurora were caused by beams of electrons colliding with our atmosphere. They've launched over lightning storms to study rare phenomena such as jets and sprites. In 1987, when a supernova suddenly appeared in the sky, sounding rockets were among the first to study it. Sounding rockets captured samples from the hole in the ozone layer, critical to understanding how the hole formed. Today, they continue to push the boundaries of what we can see and learn.
We're now joined by two other sounding rocket experts. Kathy Hesh is the technology manager for the National Sounding Rockets program, and Doug Rowland, he's the lead scientist for the Arctic sounding rocket mission that you saw at the top of the show. Now, all of you have launched sounding rocket missions before. Out of all the different kinds of spacecraft you could use, why do you keep coming back to sounding rockets for your research?
Well, for my own research, it's really to look at that region of space, which is actually about between. There's too high for measurements with balloons and too low for satellites, so that's why we use rockets. Also, you want to get the vertical profiles. My personal research is with the interface between the ionosphere and the upper atmosphere, which occurs at around 100 kilometers or 60 miles up. Some of the most important processes in geospace happen there. It's really one of the most happeningest places in all of geospace, and you can only measure it with sounding rockets. So, of course, we're going to use rockets to do that research.
Right, and as you go up and come back down, you're also able to see measurements that vary along a vertical dimension,
definitely.
right?
Right.
And we in the last video that the viewers just saw, we also talked a little bit about the ozone layer.
Yes. Okay.
Right.
Exactly. In fact, first of all, I just want to emphasize that rockets give you the vertical profiles, just as you said, up leg and down leg, which you can't get on a satellite, at least with direct measurement. But in view of the ozone comment, sounding rockets also enable us to take samples of the upper atmosphere, either in ozone or maybe in noctilucent clouds, recover those samples, bring them back to the laboratory for detailed study.
Now, Doug, I know that you've launched through the Northern Lights, and you're not the only sounding rocket researcher to do that. What is it about sounding rockets that makes them so useful or suitable for auroral research?
Well, Miles, you mentioned where we go where the science is. You know, that's one thing we do. And so the Northern Lights, you don't see those in Washington, D.C., but you go to Alaska or Norway or Canada, and you can see brilliant displays. The things about those auroral displays is they're very kind of sudden, they change, they dance around. And when they do that, you've got to be in the right spot at the right time or you're going to miss it. And so what we do is we set up our rockets, we wait for those auroras. It's almost like, you know, you're in a hunting blind or something trying to wait for that aurora to come out, and then you go. And I think the sound rockets provide an opportunity for you to kind of do that targeted research.
Right, and going along with that, you could go to all these different places, right? I mean, you're going to Norway in an earlier version, you know, one of your earlier missions, Say more about that.
Well, we go to Norway. We went to Norway with our mission because that was a particular magnetic field configuration, a particular region of the Earth that we wanted to study. But we've been launching at Wallops Flight Facility in Virginia when we study thunderstorms. We've launched from White Sands Missile Range, people who study different astronomical observations. We've gone to Peru or Marshall Islands, or just everywhere in the world, kind of wherever the science is, we go. Yeah.
Now, Kathy, you've been involved in tons of different sounding rocket missions that have come through Wallops Flight Facility. Tell us more what you've noticed about sounding rocket missions that makes them unique.
Well, sounding rocket missions really inspire innovation and ambition among the science community. They're one of the most low-cost and quick platforms that you can use to get into space. And it's really interesting to see how all the different science disciplines utilize sounding rockets to do this cutting-edge science that they do. There are about 40 to 50 sounding rocket missions in progress at any given time. Annually, we launch about 18 missions a year from launch sites all over the world. And a typical mission life cycle is about on the order of 2 years for a new mission. For missions where payloads already exist and we can refly again, they can be done in as little as 6 to 12 months, so a relatively short time frame. As I mentioned before, sounding rockets are also extremely cost effective. The average cost for a sounding rocket mission is on the order of about $2 million. And there are kind of three main things that keep us low cost. We utilize military surplus rocket motors. Those are motors that the military no longer needs or wants. We use commercial off-the-shelf components. And we recover about half of the payloads that we fly. So we'll launch them, we'll go pick them up on a helicopter or on a boat, refurbish the instruments and the support systems, and refly them again. And some of our payloads have flown 3, 4, 5 times looking at different targets of opportunity.
Wow. That's a really important point, actually. The low cost and the quick turnaround of sounding rocket missions is one of the things that makes them the place where the latest ideas and newest technology are often first tested out. A great recent example comes from the recent HI-C mission, which stands for High Resolution Coronal Imager Telescope. NASA researchers mounted this telescope on a sounding rocket, launched up into space, and looked at the sun. And when they did, they saw something that had never been seen before. Let's take a quick video view about that now.
So one of the questions in solar physics is how is the corona, or the atmosphere of the sun, heated? You want to know if it's caused by braids in the magnetic field, or is it caused by waves. The problem is that you look at the sun's corona in images and it doesn't look particularly braided. It looks kind of, combed almost. The structures that you see don't look like they crisscross or circle around each other or anything. Maybe the braids are just below the resolution of our current instrumentation. So we built HI-C, this high resolution imager, and one of our goals was whether we could see braiding or not. So we're all in the car on the way back from White Sands back to Las Cruces. I'm in the passenger seat, the PI's in the driver's seat, Jonathan Certain, and I've got my little laptop and I'm looking at the data for the first time and we see a braid. And on the drive, Jonathan pulls over, we call everybody else, we're like, we see braiding, we're so excited. And then Jonathan's like, why am I driving? You need to drive so I can look at the data. But that was our first time that we'd seen magnetic braiding, and we actually got a Nature paper from that result.
Sounding rocket missions can be developed in really quick time periods. As we mentioned earlier, sometimes that's as short as 6 months. And this really makes them an ideal platform for capturing brief events and also testing out some of the latest and newest technology. Kathy and Stephen, you guys can speak more directly to this. Stephen, you're an astrophysicist at Johns Hopkins University, and you've been using sounding rockets for your research for a long time. I understand one common feature of your missions is you're usually testing out some new tech that is being developed for bigger missions many years in the future. And you've even done crazy things like chase after comets. Could you say more about that?
Sure, Miles. Targets of opportunity are a unique niche for sounding rockets. They allow us to mount a mission on a very short time scale, say as short as 6 months or so, and follow up a unique astronomical event. I've been doing UV astronomy from sounding rockets for a number of years, going after comets in particular. Typically, when you go after a comet, you're using a spectroscopic application where you're looking through a very narrow little window to take narrow pictures of the comet in many different wavelengths. right now on, for instance, we did that in 1997 with Comet Hale-Bopp. It was a very successful mission. Later on, we've decided that it would be good to be able to sample larger regions of, around the comet, not just be restricted to the narrow little window. So we've developed a new technique based on technologies that were developed for the James Webb Space Telescope, and which is an infrared telescope, but we're moving them into the ultraviolet. And there we have, instead of one long narrow window, we have many little tiny baby windows that we can then sample larger regions of the sky and gather more information during the course of the observation that we take.
Have you tested this out on a flight yet?
Yeah, we recently got back from White Sands Missile Range in New Mexico, where we had a successful flight of microshutter array, the next generation microshutter array. It's a little bit different from what's being flown on the James Webb Space Telescope, and it's very new and exciting to be able to do this. We looked at a galaxy called M33, and we looked at the star clusters in the galaxy, and we wanted to see how the gas that was blown out of these very hot new star clusters is emerging from the disk of the galaxy and populating the circumgalactic medium surrounding the galaxy. Often this stuff will not have enough velocity, so that it rains back down on the disk and it forms clouds of dust, and ultimately adds to an enrichment of the clouds that then can form other stars, usually lower mass stars. And out of these, you get solar systems and stellar systems that ultimately form planets out of the dust. And so the dust sort of becomes us.
Oh, wow. So what was important about the new technology you were using that allowed you to see that? Like, what was the key thing about it?
The key thing about it is that it is not just restricted to one little narrow window, but it's lots of little tiny windows that we can then sample larger and larger regions and increase the region that we see. This is a capability that's been enjoyed from the ground for a long time, but the technologies that we're now developing here allow us to then bring this to space, and is the basis of many mission studies for new ultraviolet instrumentation that is projected to be developed in the next 10 and 20 year time scale.
Ah, wow. So it's like way in the future, but the stuff is starting.
We're doing the new stuff. The big missions will just have to catch up to us later on.
Wow, cool. Kathy, I understand you've been involved with some missions that are actually testing out technology that will help us get to Mars, right?
That's right. You might have heard of the NASA's Artemis mission, where we plan to send spacecraft and humans to the moon and then eventually onto Mars. Well, before we send humans to Mars, we're doing robotic missions that are going to be collecting scientific data that then tells us a little bit more about the planet and what's going on there. So, as you know, landing on Mars is not an easy thing to do. The atmosphere on Mars is significantly less dense than it is on Earth, and so landing a payload the size of a car or a small SUV coming in from supersonic velocity is incredibly difficult to do. So we recently worked on sounding rockets with NASA's Jet Propulsion Laboratory on their Aspire program. And what they're interested in doing is studying the fundamental inflation characteristics of a supersonic parachute. So we flew 3 sounding rocket missions over the course of 2 years, and they were able to use very high definition video to study this inflation characteristics of the supersonic parachute. And they're able to take what they learned from the sounding rocket flights and then design a parachute for the Mars sample return system that they're going to be developing for the Mars 2020 mission.
Wow. We're getting a bunch of questions on social media, so I'm going to take some of those now. Onab on Facebook wants to know, how fast do sounding rockets go? Maybe that's a question for you, Kathy.
So the mission we've seen earlier, Doug's Norway mission, that rocket got about to 8,000 miles per hour. So that differs from, say, what the International Space Station or the orbital rockets, those typically have to go to speeds of about 17,500 miles per hour to stay in orbit. So we're at least half the speed of an orbital mission.
Right, but that probably gives you some level of hang time when you're flying.
That's right, yeah. We want to send all our velocity straight up as high as we can so we can get our rockets as high as they can and get as much time in the space environment as possible.
Marcy on Facebook is asking, can the sounding rockets be tracked after the launch and in the place that they land? Steven, you want to take that?
Sure, yeah. Sounding rockets are often tracked with via radar or GPS, and I think you mentioned there were some other techniques that were being developed to do that as well.
Mm-hmm. Cool. Steven from Facebook is asking, how far downrange does a typical sounding rocket travel, and how are the payloads recovered?
So some of our smaller rockets can go about 60 to 90 miles offshore, and on several of our Wallops missions we'll use a recovery boat that will go out and retrieve the payload from the water and bring it back. For our White Sands missions, it's about 60 miles that they go. And again, we use a helicopter that's a land range. So we take a helicopter out and pick up the payload and bring it back and can refurbish and refly the payload. Some of our biggest rockets that we fly can land about 400 miles off the coast. And those are a little far for us to send a boat out to go retrieve. So we let those fall into the ocean and we don't recover those.
Wow. Nikita on Facebook wants to know, how much does it cost to build this kind of rocket? You mentioned a little bit about this already, Kathy, but could you elaborate a little bit more?
Yeah, an average mission cost is about $2 million, and that covers all of the labor, the parts to build the rocket motors, as well as any range costs associated with where we're launching from.
A question that we often get is, how do these rockets take clear pictures of faraway galaxies? So for one, you might think that they're moving a lot, so how do we get around that? And then as a follow-up, wouldn't it be better and easier to use a satellite for this?
Well, over the years, NASA has really developed a very stable ways of stabilizing the payload during flight. These involve using gyroscopes in conjunction with star trackers, and then often we'll fly cold gas jets in coarse and medium and fine modes to really stabilize our pointing. When we can achieve stabilities that are equivalent to the seeing limits of telescopes on the ground without adaptive optics.
Got it.
About an arc second or so.
Wow, so you can get really high resolution.
We can get really high resolution because once you get up there, you're basically stable. And as long as you have a gyroscope to keep locked onto the stars with a star tracker, you can get very high stability. And the other question was what was that?
So wouldn't it be better to use a satellite?
A satellite, yes.
Right.
Now a satellite can always have more observing time than we can get within the 6 minutes of exoatmospheric time that's typical of a sounding rocket. But what the sounding rockets really offer is a way to develop new science using new technologies and then training a next generation of scientists, space scientists, to carry those technologies and science techniques into new orbital missions. So we're really enabling these big missions that NASA is planning to do in the 10 and 20-year time frame.
Wow. The hub of all of this work on sounding rockets is on the eastern shore of Virginia at the Wallops Flight Facility. Wallops is the nation's premier facility for suborbital flight. Here's a quick video to show you what Wallops is all about.
Founded in 1945, NASA's Wallops Flight Facility on the eastern shore of Virginia is America's oldest established launch range. Over the years, it's become the agency's premier location for suborbital flight. Wallops is home to NASA's Sounding Rockets program. From the earliest designs through to launch and recovery, it all happens through Wallops. It starts with a researcher who has a science question. Engineers at Wallops then design a sounding rocket mission to help answer that question.
They have incredible engineers here who are solving tough technical problems.
They design the trajectory, machine all the parts, test the payloads, and turn it all into a flight-ready rocket. The whole process takes anywhere from a few months to about 2 to 3 years. And it always ends with a bang. Wallops supports about 20 to 25 launches a year from their home base and at locations around the world. Wherever they are, the team is there to prepare the rocket, coordinate launches, and receive the data for the mission.
Another unique aspect of the Sounding Rockets program is the involvement of students. It's really one place where students can get hands-on experience working on a space science mission. Stephen, as a university professor, you're around and working with students a lot, and I understand sometimes they're directly involved with your missions. Can you tell us more about that?
The students are essential to our program. Over the past 60 years, we've had undergraduates and graduate students. There have been over 40 PhDs granted within our Sounding Rocket program. Students are involved at every aspect of the mission development, from the definition of the science concept to the flow down of science requirements into technical requirements for the mission, and then the actual design and fabrication and procurement of all the instruments that we're going to be building. Typically it involves telescopes and optical systems, vacuum systems, and then we go ahead and involve them then with the actual planning of the flights, the integration and testing, the calibration of the instruments, and then we go to the field. So go to the field for the astronomy program to White Sands Missile Range. White Sands Missile Range offers a unique capability in that we can recover the payloads without too much problem. And they also have a system where we can actually fly the telescope during flight. So the students will be piloting the telescope over the first six minutes of exoatmospheric time that we have available to us.
So when you say fly, you mean like aim it, or?
Yeah, with our precise pointing capability, we'll have a downlink image of the stellar field that we're looking at, and the student can then use a joystick to point the rocket to the actual target that we're interested in.
Wow.
And then once
a lot of pressure.
A lot of pressure.
Yeah.
Of course, once the flight is all over, and it's over much too quickly, the next morning we come on back out, and the student goes out on the helicopter to pick it up and bring it back, and then we refurb it and go to see Kathy and say, hey, we'd like another flight.
Right, wow. So Kathy, you've been involved with a program at Wallops where lots of students are coming through and they're building and even launching their own rockets right there from Wallops. Tell us more about what that is.
Yeah, at Wallops we have programs for students from the undergraduate level all the way through grad school. In fact, over 400 PhDs have been awarded over sounding rocket research that was done on board one of our missions. At Wallops, every year we do 2 student sounding rocket missions. We partner with the Colorado Space Grant Consortium and their Rock On program, and every year they bring a group of students to Wallops Flight Facility for a week, and they build these small payloads that measure the flight environment of the sounding rocket. And at the end of the week, the last day that they're here, we launch and we recover the rocket. So in a week's time frame, these students get to see an entire sounding rocket mission from all the way from the start through launch and recovery. So it's a really great experience for them. As they graduate through the program, they can then design, build, and then we will fly their own experiments that they come up with, and we fly them on the same missions. So it's a great way to train the next generation of space scientists and engineers. And we've had over 700 students from 43 states participate over the 13-year life of the Rock On program, which is really wonderful. At Wallops, we also have our own internal internship and co-op program for the Sounding Rocket program. Over its 20-year life cycle, we've had over 200 students, and typically they're engineering students come. And they get to work side by side with our Sounding Rocket engineers. So they get to design, build, test, and even sometimes launch and see the recovery operations of our missions. Again, another great opportunity for students, engineering students, to get involved. And actually that's how I got my start in sounding rockets. So I was a undergraduate student at Virginia Tech, and they were working on a rocket program with Wallops that Wallops was sponsoring. And I got involved in the program, and it eventually led to an internship at Wallops, and then that eventually led to a full-time career after graduation. And I've been with the program ever since.
Wow, how did you get started in this? What drew you to it in the first place?
Well, as an engineering student, there is absolutely nothing better than a rocket. They go the fastest,
right.
They go the highest. The loads that they go under, the thermal, the loads, the rockets are bending. It's an engineer's dream.
Right, not a bad gig.
No.
Some of these launches do happen from Wallops, but Wallops also supports flights all over the globe. In fact, right now we have NASA teams based in Svalbard, an island in the middle of the Arctic Ocean, preparing for the next launches in the Grand Challenge Initiative CUSP. But the first rockets to launch as part of that series launched last year. Let's see a little bit more from behind the scenes of that mission.
We're in the northernmost place in the world, Ny-Ålesund, Svalbard, Norway. We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby. We're here because it's dark all the 24 hours a day in the winter, so we can have the beautiful aurora overhead, use our cameras to study it. And then it has the magnetic cusp, which is a weak point in the magnetic field. There's only 2 points like that on the Earth, and every day Ny-Ålesund rotates underneath the northern cusp.
So that mission was called Visions 2, and Doug Rowland, who is joining us now, was the lead scientist. Doug, tell us more about what Vision 2 is about, and also why you had to go all the way to Svalbard to launch rockets.
Thanks, Miles. So Visions 2 was a study of the aurora and how the aurora heats our atmosphere and causes it to escape into space. Now don't worry, we've got 5 billion years or more of atmosphere left. We're not going to lose it anytime soon. But we want to understand how atmospheric escape works on the Earth, because other planets like Mars or exoplanets, they have different histories and different life experiences. And so Mars, for example, lost a lot of its atmosphere very early on. Mars is a lot smaller than Earth. It doesn't have a magnetic field like the Earth does. So there's very differences. But we want to try to understand at our local laboratory, where it costs just a few $1 million to study, and then try to extrapolate that to elsewhere, as opposed to sending many probes to these other places.
Got it. We've got a graphic here showing Earth. Tell us what we're seeing here, Doug.
Okay, well, this is a picture of the Earth's magnetic field embedded in the solar wind. So space is not empty. You have the solar wind, which is basically the hot gas flowing out from the sun. It streams past the Earth, and the magnetic field, for the most part, deflects that solar wind around the Earth. But there are two regions, the cusps, where there's sort of a funnel, where the magnetic field has a weak point. The solar wind can stream right into our atmosphere, here and here. And those 2 points are fixed. They're always on the side of the Earth that is facing the sun, but the Earth rotates underneath them. And so if you're at these very high latitudes, 79 degrees or so, about 750 miles from the North Pole, the cusp every day will rotate right over your head, and you can launch your rocket into it if you want to study how that solar wind affects the atmosphere.
So you mentioned you were studying oxygen escaping, and we're seeing, in part of this graphic, we're seeing the solar wind coming in here, but then we're also seeing a little bit of particles coming out. Is that?
That's the oxygen, Miles. So, yeah, so this is the solar wind kind of coming in this cusp funnel, and as it streams right down in, it's hitting the atmosphere directly. It doesn't have to go through any other process. And when it does, it heats that atmosphere, gives off that auroral light, and causes that oxygen to stream out. And that's another beautiful thing about the cusp. We go there because in the winter, it's dark all the time. This is the only place on Earth where you can see aurora during the day. And that makes it really cool. We have these cameras on the ground that say, okay, this aurora is telling us where the energy is coming in and energizing that escaping atmosphere. So to see if it's time to launch or not, we don't want to waste our rocket. We want to launch when there's a bright aurora there. We think there's lots of this happening. So we have a sensitive camera down here. If it was daytime, it'd be washed out. But because it's day but dark there in the winter, 24 hours a day, we can have our camera there and know when to launch and then go.
Wow. So yours was just the first mission, though, out of a whole series called the Grand Challenge Initiative CUSP. Can you tell us more about what that is? And also, we mentioned at the top of the show that we have the next 3 launches coming up next week. So tell us a little bit more about both of those.
Sure. Yeah, the Grand Challenge Initiative CUSP is a multinational collaboration. It was developed by the University of Oslo in Norway, and it's a multinational between Norway, the US, Japan, and we have contributions from the UK and Canada as well. And the whole idea is, you can do a lot one rocket at a time, but you can get extra bonus out of kind of combining those rocket missions. You save money, you save time, and you can really leverage the science from each mission to try to learn more. For example, the Grand Challenge happened over about 2 years. It started last November. It's continuing through this winter. We have next week 3 rocket missions launching potentially as part of this Grand Challenge, and it continues through to 2020 a little bit. And the idea is we have 2 launch sites here. Normally we launch our rural rockets from Alaska, Poker Flat Research Range. But here, because we want to study the cusp, we go to northern Norway. This is the north coast of Norway, continental Norway. This is Andøya Rocket Range, which is right on the northern coast there. This is the archipelago of Svalbard. The island of Spitsbergen is here, and Ny-Ålesund, at 79 degrees north, is the northernmost permanently inhabited civilian settlement in the world. So it's got an ice-free harbor, it's got an airport, it's got polar night, 24 hours a day. It's got a rocket range. The first NASA rockets were launched here in 1997. Rob Pfaff, who you saw earlier, was instrumental in getting that developed. And then we have the Norwegian scientists who really developed that and got that going so we could work together as an international team.
Wow.
And so you can see here, these are just graphical projections of the trajectories of the rocket. There are these suborbital parabolic trajectories. We go up, and we come back down. And there's a launch site here in Nealis and a launch site here in Andreoli. And we just show the different trajectories. Some are going to low altitudes to measure certain things. This is a student rocket where students developed this. These are other kinds of rockets that are going to different altitudes. And then the TRICE-2 rocket, led by Craig Kletzing at University of Iowa, was the highest one of the ones that we went. So it just depends on what you want to study. You can see how you can tailor this to really adjust any part of this vertical range you want to study.
Wow. Tell me more about what it was like to go here. I mean, this is not, New York. This is not Washington where we are now. What is it like to be and launch from a place like this?
Well, Nealison's kind of a magical place. It's this one place on Earth that's, again, 750 miles from the North Pole. There's more polar bears than people. And there's a wonderful town there called Nealison, which is sort of a strange town. It's a private-public partnership with the Kings Bay Company and the government of Norway. And it's a research town. It used to be a coal mining town back in the day. And now they've got research going there, all kinds of research. They study glaciology, marine biology, atmospheric pollution, tectonic motion, and the aurora. And so they have various international groups come in and set up and lease space from the Kings Bay Company, and they set up their research sites, and they built a rocket range here. And so the beauty of that is they're so used to having such an international culture there that it's very open, it's very welcoming. It's dark all the time, but the people there kind of brighten it for you. It's very nice. You have these communal cafeteria, mess hall, and everything where you can kind of eat together. They welcome you into this community. We're there for 5 weeks. Some of our team was there for many months because they had to set up the launcher. They had to bring in the telemetry dishes. A lot of the Wallops guys, they go there for months at a time. Our science team was there for about 5 weeks setting up, and you really become part of that town and really part of that culture. It's just a beautiful area.
Wow. We're going to have everyone back on now. We'll take some questions from social media. So Xander from Periscope is asking, how long does it take from mission concept to launch? Probably
about 2 years for a new payload, but if we have one that's already flown and we can just refurbish and fly it again, we can do it in as short as about 6 months to 12 months on average.
Ellie on Twitter is asking, how difficult is it to build and launch a sounding rocket? That might also be a get.
So we do most of it in-house at our facility at Wallops. We do all the design and manufacturing for most of the pieces in-house, and then the rocket motors, of course, are either military surplus or we buy them from a commercial vendor. So not hard. It takes 6 months. It's only rocket science.
Yeah, right, exactly.
But no, it's certainly a fun and challenging environment to build a sounding rocket.
So Sherwin on Facebook wants to know, can you watch a sounding rocket launch, and where do I find out how and when? Where can I do that? Maybe Rob, that's it.
Okay. Well, first of all of the NASA sounding rockets are announced. We encourage everyone to watch them. You have to have a certain an amount of patience, though, because for a lot of the science missions, you're not sure when you're going to launch. You're going to launch when the conditions are just right. We usually have a 2-week window, and then every day within that window, you might have a 4 or 5 hour again, a window, which is your window of opportunity to launch, waiting again for the science conditions to be just right. I should point out, though, that if you're on the East Coast, you're welcome to go to Wallops Flight Facility to watch launches there. If you're on the West and up north, you can go to Alaska to watch launches into the Aurora from Poker Flat Research Range or White Sands. We also do all a majority of the launches are live streamed. Yeah, so you can actually, you can see them on nasa.gov/Wallops. So again, we really encourage the public to get involved.
Got it. Christine on Facebook is asking, how is data retrieval accomplished? So, for example, is it collected during flight, or do you have to wait till the rocket falls back down? Maybe Stephen, you want to take that one?
Yeah, no, we have real-time telemetry from the rocket. It happens on board. It's turned in all your housekeeping, analog channels, and your digital primary science data is turned into ones and zeros and put into a great big matrix. And this matrix is then sent down on the ground via S-band radio waves and translated by a ground station, and we have real-time contact. And sometimes they go ahead and record if they have very high data rates on board. But for the most part, you have real-time contact, and you know almost instantaneously what has happened.
Got it. And that's what telemetry is, right? It's the sending of the information back down to Earth.
That's correct, yes.
Cool. One of our Facebook followers is asking, in your opinion, what's the most important thing we've learned from the Sounding Rocket program, and what is the most interesting question you still hope to answer? This one is a free-for-all, anyone, yeah.
Okay, maybe I could start
Yeah,
off,
yeah.
and the others could pitch in. We've had so many discoveries from the rocket programming. I always think back to the Aurora, how it was sounding rockets that the determiner discovered that it was beams of energetic electrons coming down the magnetic field lines, interacting with the atmosphere to actually cause the Aurora. But it didn't stop there. I mean, we also did so much more and are doing so much more research with the Aurora as far as electric fields and waves associated with the Aurora, how does the Aurora affect the chemistry of the upper atmosphere, the heating, the ion outflow that Doug was talking about. So it's a whole new field, and we keep getting more, we keep being led on to do more follow-on missions to go after the important processes that we're discovering. We've also looked at noctilucent clouds and the aerosols that have ice sublimation to create those clouds. Those were discovered on sounding rockets. Lightning studies, we've launched over thunderstorms, and we've discovered that when there's a lightning burst, a very large electric field associated with the lightning pulse, so to speak, goes up into space, and that actually can do does heating, and it's not just waves associated with the lightning, but these electric field pulses are very important. We've looked at instabilities associated with the electrojet. That's a region at the base of the ionosphere, at the equator, and also in the auroral zone. We've looked at turbulence in space. It's so important for space weather because it causes scintillations of radio wave signals, important for navigation. Make sure your GPS is giving you the right information. It could be altered, and is altered by turbulence in the ionosphere, and we've used rockets to study that. So there's really a tremendous amount being done in geospace. Also, in the astronomy and solar, just getting above the atmosphere has allowed us to look at wavelengths that are normally absorbed by the atmosphere. In fact, the whole field of UV astronomy was started with sounding rockets, as was X-ray astronomy. So, and the work being done with solar, the very high time resolution. So it's really, we're just getting discoveries and discoveries. It's really a tremendous program.
Wow. This is a question probably for Kathy. What fuel do sounding rockets use?
We use solid propellant rocket motors, so it kind of has a hard rubbery texture to it, and it carries all of its metallic ingredients and its oxidizer and binder all together, so solid propellant.
Another one probably for you as well. What happens to the rockets that fall into the ocean?
They become homes for fish. They fall into the ocean. They're just metallic shells, and they sit there and become homes for fish.
It's actually like a good home for fish, like they can live in there?
Yeah.
Wow. This is for Doug. Regarding our oxygen leaking into space, does this sound scarier than it actually is, or it is actually terrifying?
It sounds much scarier than it is. We've got billions of years of oxygen left. Again, it's a very slow leak. It's like a pinhole for us. But when you look at other planets, it can be a giant gust that's blowing their atmosphere away. So we just want to see how that pinhole works here so we can understand the hurricanes elsewhere.
It's a really exciting time for sounding rocket research. Head to @NASA Sun on Facebook and Twitter for updates on the next 4 launches that are part of the Grand Challenge Initiative CUSP. Thanks to all of you for joining me, and for viewers at home for tuning in. Bye-bye. There's one thing that stands between us and the harsh environment of space: our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of 2 regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is, how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket and only 15 minutes to use it. I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation from today and try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
Its continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chalmar? We'd like you, as soon as you see an indication the cusp is moving close, to move the radar dish if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
No. Probably about a 60% chance of launching.
When we started seeing this really good data This clock started counting down, and that's when everyone realized, this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
The jet stream may be the best known high-altitude air current, but it is not the only one. Measurements from the last 60 years and observations of the movement of Space Shuttle exhaust indicate that there is a region between 62 and 68 miles up that experiences wind speeds of 200 to 300 miles per hour. At that altitude, right on the official boundary of space, it is extremely hard to measure the wind because the atmosphere is so thin. It is also high enough that only powerful rockets are capable of reaching it. The ATREX, or Anomalous Transport Rocket Experiment mission, is launching to study this ultra-high altitude wind over the eastern seaboard of the US. It will consist of 5 rockets, launched within minutes of each other from the Wallops Flight Facility in Virginia. As each rocket rises above 50 miles, it will release a chemical tracer into the upper atmosphere, dispersed over a horizontal range that extends approximately 340 miles east-southeast from Wallops. The tracer is trimethyl aluminum, which glows when it reacts with oxygen. The products of this reaction are aluminum oxide, carbon dioxide, and water vapor, all of which are found in the atmosphere. Cameras positioned in North Carolina and New Jersey will watch for the glowing trails, which will reveal the wind's direction and speed. Understanding the patterns and causes of this wind will help NASA and private corporations with future high-altitude, low-orbit missions. It is possible to have 5 rockets for one mission because ATREX is using sounding rockets. Sounding rockets are small, powerful rockets that usually carry a payload up and then back down to Earth. They can't carry much weight, but this makes them far less expensive and a good way to make observations at the edge of space.
I think the students are here really to know what it's like to build a sounding rocket payload.
Really what NASA does best is, not only inspiring, but connecting people with space. So Rock On is just one of those steps that create those openings for students around the country to have some real-world, hands-on experience with a connection to an actual space flight.
I think one of the most rewarding things for me is seeing the transformation of the students throughout the workshop. By the time it's Monday or Tuesday and we're getting ready for integration, they're high-fiving the helpers all know them by name, and it's just great seeing this transformation of someone who's so closed off to someone who's completely broken out of their shell.
When I interact with students, I want them to feel comfortable, I want them to have fun, because I feel like that's when they're going to learn their most. It's not uncommon for me when I'm working with students to be in costume. Today even, I'm Captain Picard from the Starship Enterprise. Try to break down walls when I'm working with students and faculty, but suddenly the focus is on the crazy guy and not, do I belong here? So they're most comfortable, ready to have fun, but also ready to learn.
We have students end up soldering on resistors and capacitors and LEDs and a bunch of other connectors, and they build all of that up. We run them through code. Monday, we finish up the coding, and then we put everything on the plate, do a final check-in, and we integrate to the canisters, and it's just a whirlwind of a day. There are students here who aren't engineering students, or we're just majoring in physics or chemistry, and we had a couple humanities people here. And in the end, they came out with a rocket payload. So it doesn't really matter where you're from, what your background is, you can do it.
It's just a really unique experience, I think. Everyone should do it, even if they're not interested in engineering or anything space related. It's just cool.
I haven't been to a launch before, but I have a feeling that it's going to be kind of surreal. I've seen it on TV, so seeing it in person is actually a blessing.
I'm expecting it to be loud. I'm expecting it to be big, and I'm expecting it to be fun.
Oh, so excited. Like, every time I think about it, my heart starts racing, and I'm like, okay, yes, I'm waiting for that day.
Launch is definitely the highlight, to see that thing ignite. So everyone still counts, 10, 9, 8.
7, 6, 5, 4, 3, 2, 1, 0.
It's hard to take your eyes off the flame, but if you do, just for that moment, you see life happening all around you. Their brains are recording this for the rest of their lives. They're experiencing something that they've worked hard for. And to me, that's almost as exciting as watching the launch.
I also feel as if you can learn the stuff here, you're ready to take the next steps towards what you want to do in the future.
I think just having, a student who clearly been affected by Rock On in this way in terms of their personality, in terms of their confidence level, kind of speaks to the success of the program. It doesn't really matter if your experiment comes back and it didn't work. We like to make sure that people are comfortable here, and I think that we do a good job doing that, and everyone leaves here pretty satisfied with the program. So I can say whenever I want. Okay, rock on!
Rock on!
Rock on!
Rock on!
Constantly shielding us from the sun's high-energy particles is the Earth's magnetic field. Many imagine this field as a circle slightly larger than our planet, but it's actually shaped like this. And near our north and south poles, there is a cusp, a point where two branches of a curve meet. It's here that the magnetic bubble that surrounds us dips inward, creating a funnel of magnetic lines that touch down to Earth. This funnel allows the sun's high-energy particles to race toward our planet and deposit themselves in our ionosphere, 80 to 800 kilometers above Earth. We can even see the result. They create beautiful aurora, similar to the spectacular displays at night, but on the day side of Earth, and only visible to the naked eye during the long polar night. Now, scientists who want to learn more about effects of these particles are embarking on a special initiative that is taking place from December 2018 to January 2020. In a coordinated effort between multiple countries to understand the physics of the polar cusp, scientists from NASA and the US, as well as from Japan, Norway, Canada, and Great Britain, have launched the Grand Challenge Initiative, CUSP, a series of sounding rocket missions that will provide the data needed to conduct 9 unprecedented studies of near-Earth space at the polar regions. This series will help scientists glean answers to a number of questions about the cusp. Why is our atmosphere leaking out into space from the cusp? How and why do the turbulent hot patches of dense plasma that exist inside the aurora region disrupt global communications?